All right, let's jump right in. Today, we are cracking the code on a concept that secretly runs pretty much the entire world of calculus: continuity. You know, it's all about those smooth, predictable, unbroken paths. Let's get to it. So let me ask you something simple. If you look at a graph, could you trace the whole thing from start to finish without ever lifting your pen off the paper? Seriously, this little pen test is the gut feeling, the intuition at the heart of everything we're about to explore.
And believe it or not, that's really it. That pen test isn't just a fun little doodle. It's basically the visual definition of continuity. It means the function has no gaps, no sudden jumps, no weird holes. It's just a perfectly unbroken line. And today we're going to figure out the official rules behind it.
Okay, so to go from that gut feeling to, actual mathematical certainty, we need a formal definition. But don't worry, it's not that scary. Just think of it as a simple three-point checklist that any function has to pass to be considered continuous.
So here are the three big rules. First, the point you're actually looking at has to exist. I mean, you need a destination, right? Second, the path leading to that point from both the left and the right sides has to be heading to the exact same spot. And third, and this is the real kicker, the path has to actually connect perfectly with the destination. The place you are headed is the place you actually land.
Let's zoom in on that second rule for a sec, the limit. A limit isn't about where the function is at that exact moment, it's about where it's going. Imagine you're walking along the graph from the left, and a friend is coming from the right, both heading to the same x value. For that limit to exist, you both have to be zeroing in on the exact same height. If you're heading for different places, well, the limit just doesn't exist.
So what does this all boil down to? It's this one single, really beautiful equation. All it says is that the value the function is approaching, that's the limit, has to be the exact same as the value the function actually has at that point. When those two things match, you've got continuity.
But, of course, not all functions are so perfect. When a function fails that three-point check, we call it discontinuous. And these breaks, these kind of glitches in the code, they come in a few different flavors. Let's explore the four main ways a function can fall apart.
So, you've got a few main culprits. A removable one is like a tiny pothole in a perfect road. A jump is like the bridge is out. The road just stops and reappears somewhere else. An infinite break is when the function just launches itself up or down to infinity. And oscillatory is where it just goes haywire, wiggling like crazy. Let's look a little closer at that pothole, the removable discontinuity. With this one, the path is perfect. The limit from the left and the right totally agree on where they're headed. The only problem? When they get there, the destination, the point itself, is just gone. This is actually the easiest kind of break to fix. Now compare that to a jump discontinuity. This is a whole different beast. This isn't a simple pothole, it's a cliff. The path from the left leads you to one height, but the path from the right is way up, or way down, at a completely different one. Since the left and right sides don't agree, there's no way to fill in the gap. That bridge is out for good.
Okay, enough about broken functions. The really cool part is what continuous functions let us do. Their smooth, predictable nature unlocks some seriously powerful tools in mathematics.
And that brings us to the star of the show, the intermediate value theorem, or IVT. Now, I know it's a bit of a mouthful, but the idea behind it is actually pretty profound. It guarantees that a continuous function can't just skip over values. It has to hit every single point between where it starts and where it ends. Think of it like this. You're in an elevator. If the ride is a smooth, continuous journey, you can't magically teleport from the first floor to the fifth floor. You are guaranteed to pass through the second floor, the third floor, and the fourth floor on your way up. That's the IVT. No cheating, no skipping values. So why does this matter? Well, one of its biggest uses is proving that solutions to equations, what we call roots, actually exist. If your function is continuous and it starts out with a negative value below the x-axis and ends up with a positive value above it, then the IVT guarantees it had to have crossed zero somewhere in between. And that crossing point, that's your root. All right, theory is great, but let's get our hands dirty. We're going to take a function with one of those classic pothole discontinuities and use everything we've just learned about limits to fix it. So here's our function, and you can see right away we've got a problem at x equals 3. If you try to plug 3 in, you get 0 in the denominator, and we all know that's a huge no-no in math. It's a hole. So our mission is to find the perfect value k to define for f of 3 that will plug that hole and make the whole function smooth.
The key here is good old-fashioned algebra. We can't plug the number in, so we have to simplify first. Let's look at the top, x squared minus 9. This should look familiar. It's a classic difference of squares, and it factors out perfectly into x minus 3 times x plus 3.
And here it is, the magic moment. The x minus 3 on the bottom, the thing that was causing all the trouble, just cancels out with the 1 on top. And what are we left with? The much friendlier, much simpler function, x plus 3. Now this new function is identical to our original one everywhere except at that one missing point. So now we can finally figure out the limit. We can ask, what value was our simplified function approaching as x got closer and closer to 3? Well, now we can just plug the 3 in. 3 plus 3 is 6. That's the destination the path was heading towards all along.
And there's our answer. For a function to be continuous, the value at the point has to equal the limit approaching the point. Since the limit is 6, we have to define f of 3 as 6. So k equals 6. We've officially plugged the hole.
Okay, let's do a super quick recap. Continuity is all about that 3-point check. The point exists, the limit exists, and they have to be equal. Remember, some breaks are like potholes you can fix, but others are like jumps that you can't. And the intermediate value theorem? That's your secret weapon for proving a solution exists, because it guarantees a continuous path can't skip any values.
So we spent all this time talking about smooth, predictable, continuous paths. But here's a final thought to leave you with. In the real world, from quantum physics to the stock market, where do you think the sudden jumps, the breaks in the code, actually tell the more interesting and maybe even the more important story?